Hey, calculus seniors, how we doing? It's Mother's Day, Sunday, and my mom lives in a red county, so can't go visit her. So we're at home today, and here I am making a calculus video for you for the week. And it was snowing, so I had to put on my fur hat because it's cold. It doesn't feel like May. So if you see on the board behind me, we're going to use integration, use the integral to find volume. And then over here it says the washer method. And washer method, that has nothing to do with a washing machine. So I hope that didn't pop in your head. What does it have to do with? It has to do with one of these. A washer. Okay, over there in my shop I got a whole drawer full of these things, all different sizes. So what's a washer? What's a washer? You know, a washer is two concentric circles. What's concentric mean? Same center. It's a donut. And what we're after is, we don't care about the hole in the middle. We care about, like, on the washer, the metal part. Like maybe, we want to find, what's the quantity of metal that it takes? Well, this is 3 dimensions. Even though it's really thin, that's probably only about 1/8 of an inch thick. 1/8 inch thick. So remember, volume, 3 dimensions, length times width times height. How do you find the area of a rectangle? Length times width. How do you find the volume of a box? Length times width times height. Well, now those formulas are good, and there's a bunch of other formulas that we probably talked about in geometry. You can find the volume of a pyramid, the volume of a cone, the volume of a sphere. All of those shapes are like, there's no holes in them. Okay? So like if I said, volume of a box, or volume of a cylinder. Okay? Here's a cylinder. Volume of a cylinder, volume of a cylinder, pi r squared h. Pi r squared times the height. A cone, pi r squared h divided by 3. It's 1/3 of that. Volume of a box, here's a wooden block. What's the volume of this rectangular box? Well, length times width times height, 3 dimensions. So really, I know you kind of think when you were in grade school, they said, well, volume is how much something holds. Like here's a cup, here's a box, how much does it hold? But really now what we're talking about is that 3-dimensional object being solid. How much wood is in this cylinder? Okay, how much wood is in this cylinder? How much wood is in this block of wood? So these aren't really holding any liquid or anything. There's nothing in there. They're solid. So if we have a solid, how much material makes that solid? But you're going to see that our shapes are going to look really weird. And I don't want you to fixate on what these things are going to look like, because the calculus process is no more difficult than things that we have already done. So let's start out here. If I said to you back in geometry class a few years ago, what was it, 2 years ago we shared geometry class, and I said if I said to you, find the shaded area of this shape, what is that? It's a washer. It's a donut. Technically, in mathematical lingo, we don't call them donuts. We call them a torus. If it's 3-dimensional, so when you look at a donut, next time you have donuts, say, hey, pass me a torus. T-O-R-U-S, torus. That's what that shape is called. But donut's okay, I guess. How would you find this area? Well, here's what you would do. These are 2 circles. You would probably do this. You would say, well, Mr. Lipscannon, from the center to that outside edge, boom, that's radius. And then you would say, well, the center to this smaller circle, that's a smaller radius, so we'll go lowercase r. And then what would you do? You would do this. You would say, well, the area of that shaded region is pi r squared, the big R, minus pi, the little r. That's what you would do. So we've already done that problem. Well, that problem is the basis for this calculus method called the washer method to calculate volume. Because what are we going to do here? We're going to look at a three-dimensional shape. It's going to look like this, sort of, kind of, sort of. Okay? So it's going to be like a tube with a hole through the center. All this would be shaded. There would be a hole in the middle. It would be like me taking this cylinder and drilling a hole right through it. What are we after? How much wood's there? We don't care about the hole. The hole's gone. We care about how much material. So people that are going into engineering, people that are going into ceramic sciences, material sciences, which is a really big field nowadays. If you watch Big Bang Theory, Howard Wolowitz would probably be very interested in finding the volume of these different objects, because it's how much stuff is there. So this is kind of what, we take that washer, but we make it longer. So now it's like a straw, or it's a tube, or make like a piece of pipe. Okay, so how are we going to do this with calculus? Well, I want you to remember that. Let's take a look here. Let's take a look. If we have our graph. So now we'll put a line here and a line here. And let's say this line is f, the function f of x, and let's say this line is the function g of x. And if I told you, hey, I want to find the area between them from point A to point B. If I gave you that problem, that problem could have been on your quiz last week, which, by the way, by now I've graded most of those quizzes and returned them, and everyone did exceptionally well. And I was really, really excited to see that a few of you tried the bonus and you nailed it. And because it had trig and it had to be radical form, so I know there was a few people that nailed it, did very well. So good job, everybody. If you had to find this area, this is what we would have did. Left to right, remember, left to right. The boundaries of our integral. And how did we set this up? We said top minus bottom, right? We always went top minus bottom. So what's the top function? In this case, it's f of x. Minus the bottom function will be g of x. Don't forget, our differential has to be there, and every integral has to have the dx on the end. The differential's got to be there. So this is so far we talked about geometry. Two areas of a circle, pi r squared minus pi little r squared. Now we have area a different way. We have the area in here, which is represented with our calculus equation. Well, what does that mean here to find volume? How are we going to find volume? Well, if we're going to find the volume of this thing, what we do is we have to imagine we're going to rotate this sucker around the x-axis. So we are going to rotate about the x-axis. Okay? And when we spin that shaded region, it's going to look three-dimensionally like what I drew up here earlier. Okay? It's going to look like that. It's going to be a tube, or a pipe, or a straw. So if I just slice the end of it, what does it look like? It looks like a washer. It looks like this donut shape. It looks exactly like this thing that we found the area of in geometry class. It looks exactly the same. So how are we going, if we're rotating this around the x-axis, well, somehow we have to get volume out of it. So we're going to have to modify this area formula just a little bit. Just like if you're doing the area of that's length times width, we have to add something to make volume length times width times height. So just like that, which you probably learned like length times width times height in 5th or 6th grade. Plus we did it in geometry class. You probably did it in 7th and 8th grade too. So we have to add something for the volume. So here's our formula. That's going to form the basis. We're going to use this formula along with this. And we're going to extract a formula for the washer method. So what we're going to do, if we're spinning that, this top, really, if that becomes 3 dimensions, that top is now the outer. Because if that's 3 dimensions, the first radius you encounter, now that I think about it, folks, I probably should have drilled a hole through here so you could see it. I apologize. The first radius you encounter is the outer. That's the f of x. So now it's outer minus inner. Because the inner would be in here. Right? All that would be gone. We'll just pretend it's not there. Okay? So the outer minus the inner. Well, here's the problem. Let's see. Outer minus inner. That's no longer, I think I can erase this drawing down here because you've seen it now. Outer minus inner. Let's kind of talk about this a little bit. How did we find the area of that big circle? How did we find the area of that big circle? Pi times big R squared. We subtracted the inner circle, right? The inner circle, because g of x would be the small r, so pi little r squared. See that? Folks, if I have a point here, let's say I have this coordinate right there, boom. If I bring that point down here, boom, that would be x. If I bring that point over here, well, yeah, it's y, but since we're talking about it as f of x, that would be f of x, right? So that coordinate would be x comma f of x. The same thing here. This would be x comma g of x. So guess what? The big R, the outside radius, the outer radius, and the inner radius are represented by what? F of x and g of x. Because this height is the distance from here up to that f of x, or the distance from here up to this g of x. So guess what? The big R is going to be f of x squared. Why is it squared? Because it's the radius squared, because it's an area. Minus pi times g of x squared. There's my integral from a to b. dx is on the end. We can simplify. The fact that we're going from a to b gives us that third dimension. Okay? Because now we have like a whole bunch of little slices of these. Now we have a whole bunch of these. If I go over in my drawer and I take a whole bunch of these and line them up, guess what? I'm going to get a tube. It's just like if I took this cylinder and I went to my bandsaw, I started slicing little sections off, I get a whole bunch of little ones. Well, those little ones stacked up to make 3 dimensions, that's here from A to B, right? That's how far across we're going from A to B. What can we do to simplify here? There's a pi in front of there, and there's a pi in front of there. What do math teachers always preach to you? What have I always preached to you? Simplify before you do stuff. It makes your life easier. Simplify. Pull a pi out. Hey, What kind of number is pi? That's right, I hear you. It's a constant. Guess what? If I pull that out, boom. I factored the pi, now it's in front of the f of x squared minus g of x squared. I still have my integral there, and of course it's going from a to b. I'm sorry, I'm running out of room, because I'll erase this and rewrite this so you can see it. Folks, pi is a constant. And since we started integration in February, what have we always said we can do with any constant in any integral problem? What are we allowed to do with it? Where are we allowed to put it? I hope you're answering with me. Pi's go where? Where do constants go? Constants go out front. We're allowed to take them out front, and then we can just put them in at the end. And that's exactly what we're going to do here. So the washer method, this pi is going to go out front. So it's going to go pi here, boom. I'm going to rewrite all this. Okay? I'm going to rewrite it right here. Washer method, boom. Volume, V, equals pi times the integral from a to b, f of x squared minus g of x squared. Differential dx. Pi is a constant. A is what? Left boundary. B is what? Right boundary. F of x, this is the outer radius. G of x is what? The inner radius. I'm using outer and inner radius because it's, what method is it? The washer method, right? There's an outer radius and an inner radius, right? Up here in this circle. When we're doing these problems, you're not going to be able to graph these things. You're not going to be able to draw them in 3 dimensions. You're going to be drawing them here. They're just going to be given as 2 functions. And the rotation, that takes imagination. And if you can't see what they look like, I don't care. Because you know what? Some of these, I can't see what they look like either. And some of them are so tough to draw, it's crazy. So I don't want you to think of it. I want you to understand that it is an outer and inner radius, but I don't want you to think of it as an outer and inner radius. You know what I want you to think of? Just like before, top minus bottom. Okay? So, why is it out? Because we're spinning around the x-axis. It's a rotation. Mr. Lutzkanen, can we spin around the other axis? Hey, yes. If you want, we can rotate around the y-axis. Mr. Lutzkanen, do we have to restrict ourselves to the x and y axis? Can we spin around the line y equals x because that'd be cool? Yeah, we can, but we're not gonna. If you want to rotate this shape around the line y equals x, go ahead. If you want to rotate it around the line y equals 1/4 x minus 77 over 8, go ahead. You can rotate around any line that you want. We're only going to rotate around the x-axis because that's the simplest one. And really what I'm after here is you understanding the process. You're not all going to be engineers, so that doesn't matter. Plus, if you're going to be an engineer, you're going to get to all that stuff in probably your third year of calculus in college anyway. That kind of goes beyond high school. So we're only going to do x-axis. So let's do one problem, and let's get there. And let's see what it looks like. And you're going to see it's not really any more difficult than what we just did on that quiz. So as I erase here, I hope everybody's doing good. The weather's been certainly crazy. It's been snowing, and you know, you get one nice day, and it seems like we get four really bad days of weather, gloomy days. Hey, is it just me, or does it seem like since we're out of school, we've only had sun maybe 1 week, total, if we add up all the days? That's what it seems like. It's been very gloomy and dreary. So let's do this. Find the volume of the solid rotated about the x-axis, because that's the only one we're going to do, there's the line y equals x, and the line y equals 1/2 plus x squared. And what we're going to do is we're going to say bounded by x equals 0 and x equals 2. And in just a second, you're going to see why I gave you a boundary. A lot of these volume problems will give you a boundary. What's the boundary? That's your left to right. So we already have our left and right. Why? Why do we have a boundary value? Well, listen, folks, if we give you a boundary value, it makes the problem easier because I'm already giving you two components. You don't have to go to your Inspire and find the intersection because, guess what? These two functions, they don't intersect. And we're going to see that here in just a second. So, let's graph this. Y equals x. There it is. This is y equals x. I'll put a little arrow going right to there so you can see. That's y equals x. What's y equals 1/2 plus x squared? Maybe you don't like that half coming in front. Maybe you rather this. X squared plus 1/2. They're both positive, so we can put the x squared first. What's x squared look like? Well, you should know that. That's easy peasy. That's a parabola. But what does the 1/2 do? Think about it. Maybe you know the answer. What does the 1/2 do? Yeah, it's going to raise it up. It's going to take that parabola and shift it up. How far is it going to shift up? 1/2. Very good. So, if this is 1, there's a half. Now we have this parabola. So, this is that equation. So notice now, they don't even intersect. Hey, these two functions, they don't even intersect. Look at that. Craziness, they don't intersect. That's why I gave you this bounded by x equals 0 and x equals 2. Because where are we going to go from? We're going to go from here, x equals 2. So there's 1, there's 2. We're going to stop at 2. So if I go, oh, that's way up there. So we're going to be finding all of this. Now that's like if you did area, you'd find that area there. We're stopping that there. They don't intersect, so you don't need to type this in your calculator and find an intersection. If you were finding the bounded area in your calculator, you can find the bounded area there, but there's no bounds. You'd have to give it x equals 0 and x equals 2 because there's no intersection. So we're going to spin this. Why are we going to spin that? Because the volume is being rotated around the x-axis. This solid is being rotated. So what does, listen, I'm going to say this. Trying to picture what these things look like is tough. Do you need to know what they look like? No, you don't. Drawing them is even tougher. Do you need to draw them? Absolutely not. This, boom, comes in here. This swoopy part, good math term, the swoopy part. Look at that. Coming in like this. Swoopy. It's swoopy. Alright. Now, that's been spinning. So this emptiness, that empty triangle, that's like a hole in the middle, but it's not a round hole. It's sort of round. It decreases and goes to nothing. So what does this kind of remind me of? That swoopy part comes out. You know what this reminds me of? Reminds me of a megaphone. So if you look at a megaphone, someone shouting through a megaphone, that megaphone kind of looking like this. But we don't need to really care about that. Let's just set this up and let's get the calculation going. Okay? So that's being rotated around the x-axis. Let's set this up. Volume is the integral left to right. Well, what's left to right? 0 to 2. F of x, that's the top. It's the outer radius, but think of it as the top, so it's the same as before. Which one's on top? 1/2 plus x squared. X squared plus a half. X squared plus a half. Parenthesis. Minus. What's the inner? Top minus bottom. What's the bottom? Y equals x. Dx. If you're looking at that and you're saying, I think you missed something, you're right. We have one last thing to do. What did we do with those two things to make it volume? Right there is just the area. That's the last unit's problem, area. What do we do to make a volume? We square these, and what goes in front? Our good friend pi. And I explain where the pi and the squareds come from. In this case, those two squareds, they don't have anything to do with Pythagorean theorem. They come from the volume of a circle being pi r squared. So, and I already explained all that. So let's do this. Now, what are we going to do first? Before you would do the integral, we got a foil. Here's a foil. Mr. Litzcan, are we going to ever have the foil over there? Yeah. In this problem, we don't have to. Where are you going to make a mistake? Foiling, and then what are you going to have to do here? Boom. That negative, if you had to foil this, that negative would have to get distributed through. So please be careful. I will highlight that again. I'll circle my arrow because that's a place where people make a little mistake. So let's start. Let's simplify first. Let's FOIL x squared times x squared, x to the fourth. 1/2 x squared plus 1/2. We got 1/2 x squared plus 1/2 x squared plus, what's a half times a half? Half times a half. I can't hear you. It's a quarter. What's over here? Minus what? Minus x squared. We haven't taken the integral yet. Can we simplify that? Oh yeah. 1/2 x squared plus 1/2 x squared. These two come together and make what? 1 whole x squared. And guess what? That cancels with that minus x squared. So what this turns out to be over here, pi 0 to 2 x to the fourth plus 1/4. Look at that. This whole mess just simplified to that. We've done problems that have been much more difficult than this integral. So let's execute this integral. Okay? The integral of x to the fourth is what? X to the fifth over 5. Plus, what's the integral of 1/4? 1/4 x. We're going to evaluate that from what? 0 to 2, and what's out in front? A pi. Isn't it wonderful when you got to plug in a 0? Isn't it wonderful when you have to plug in a 0? Plugging in a 0 is like the most beautiful thing ever, because all you have to do is just, look at, you're going to have 0 plus 0, boom, that goes away. All we have to worry about is plugging in the 2. Pi 2 to the fifth, I'll put this in parentheses, 2 to the fifth over 5 plus 1/4 times 2, boom. What's 2 to the fifth power? You should know that. You had NP, he made you memorize those. It's 32. This is 32 fifths plus 2/4, that's a half. What's in front? Pi. You remember the easy way I taught you how to do that? And everybody, remember this was a long time ago, back in probably September. I said, well, it's just crisscross math, but they don't teach you this in elementary school. And why they don't teach it, I don't know. I honestly don't know why things get so complicated. What's 32 times 2? 64. What's 5 times 1? 5. Crisscross across, so diagonal, diagonal, and then 5 times 2, 10. 64 plus 5, 69 over 10. Oh, what was out front? Don't forget the pi. Put the pi in the end now. Instead of having the pi out front, put it on the end. 69 pi over 10, that is the answer. So 69 times pi, that's roughly 70 times pi. 70 times 3, a little bit bigger than 3, so that's 210. A little bit bigger, 210 divided by 10. This is a little bit bigger than like 21, probably closer to 22. So as if you're trying to estimate it. So anyway, diagonal, cross, we talked about that many times, and 69 pi over 10. So that's it. I'll step aside. We'll let the camera run for a few seconds so you can see the whole board. And obviously you can go back and rewatch any portion of this anytime you want. There's also, remember my office hours, Monday, Wednesday, Friday, 9 to 10 in the morning. If you need help, you can click the link. It's on your Google Calendar. It's also on our Google Classroom. And also, if you need more help, if you Google finding volume with the washer method in calculus, you will probably have an ample supply of other videos. But I'm going to guarantee you one thing about those other videos. Actually, I'm going to guarantee you two things about all those other videos that might come up. Number one, no one's going to have a hat as cool as this. And number two, no one's going to have a beard as cool as this either. So I'll step aside so you can see the whole board for about 2 seconds, and then I will sign off. So see you later.